Okay, let's talk a little bit about the history of computing. Okay, why that is interesting? Okay, it is interesting so you have knowledge about the stuff you're doing, the very stuff you're doing, so you know where it came from. But okay, the reason why, probably for every theoretical module you have the history session, is because of course it gives the lecturer a way to follow linearly the progress of thought that created a discipline, right? And that is good for students because, of course, you have to start with the simple concepts and then you elaborate. Okay, so you can divide the history of computation in an ancient time, the medieval one, Renaissance, and then the modern days with the Industrial Revolution, and well now, so the present days. So the history of computation is really the slow realization that you can split symbols and meaning. Well, of course, first you have to figure out the fact that you can use symbols, and that is done in the ancient times. What's a symbol? So you have something, you have a meaning, an idea, okay? And you put it down on some hardware. It can be a piece of paper, clay, you know, and it doesn't really matter. It's a way to encode information well, on a support, okay? So that you can interpret that symbol and get back to the meaning, okay? So the history of computation, first you have to, have the symbols, but once you have the symbols, you have to realize that symbols and meaning belong to different systems, okay? I will show you how that is done. So in the ancient times, as I told you, there's the history, the beginning of civilization. Civilization starts when humanity actually understood that information can be encoded in symbols, okay? So from that you can write, okay, and of course then there's a huge explosion of culture, and really the invention of writing is like, it's more powerful than the invention of the computer, meaning that when people started writing, really the civilization could expand, because you can have a set of rules which are written, which can be, if I have a city here and I want to control another city there, the only way I can do it efficiently is by writing, okay? It's exchange of whatever, letters, clay, tablets, okay? So the civilization needed this invention. Okay, but why is it important to us? Because all computation is symbol manipulation. All computation is taking a string of symbols, doing stuff to the string, and getting another string of symbols. That's all computation is about. At least, that's the state-of-the-art understanding of computation. When we talk about digital computation is just symbol manipulation. Okay, so the first ones to understand that you can use symbols were in Sumer, right? Mesopotamia, yeah. I think it's in the Sumer area. And yeah, initially their symbolization were really crude, okay? So if I had an object, I had a symbol for that object. If I have a chair, I have a symbol for a chair. Maybe if I had a blue chair, I have a symbol for a blue chair. If I had a red chair, I have a symbol for a red chair. So of course there's an explosion of symbols. We need to use a lot of symbols to talk about this reality. But there's already this is the beginning of computation. You have hardware and you have software. The software is the symbols and the hardware is the clay in this case, right? So slowly by slowly, I think some smart guy understood that it's a really efficient way to symbolize, to just create a symbol for each object. So they're starting having this syllabic encoding, right? So an example is exactly like that. Okay. I have a symbol for I have a symbol for deer, and I put them together and I have a symbol for idea, so I don't need a third symbol, right? I just need two. So they started using this syllabic writing, which is already a great feat of intellect, because you're abstracting away from the symbols. Okay, symbols are not so tied to the physical reality you're trying to describe. Okay, now there's a layer of indirection. You have to compile. You have to compile this. You know, the new symbol, the new words have to be compiled. You have to actually read idea and say idea. You do it in your mind. Okay, this is already a great feat of intellect. Now, of course, for now this seems so easy, but it is not. So okay, there's a process. So we get further and further away from the actual reality. So instead of syllabic writing, we will have phonetic writing, so that each symbol has a phoneme. Okay, each symbol describes a phoneme. So you know, you even go away from the original. In the original syllabic writing, you read the actual object that the symbol represents. Okay, in this case, there's no object. There's a sound. What's a sound? It's nothing. So they created the phonetic writing, and the Greek improved on that and created the first alphabet. Yeah, first alphabet. Some guys were joking before about the Greek derivations of some words. I don't know if they studied Greek or something, but yeah, okay, yeah, I got that. Yeah, so they created the first alphabet. Now, Seraphim wrote here that alphabetic reading is mechanizable, but I don't think English is really that mechanizable, because in English you have a really weird system where the signs on paper don't correspond to sound in any way. I don't know, it's really hard. And I learned English mostly by writing, right? Because when I lived in Italy, I had access to manuals. I studied, you know, technical stuff on manuals in English, because of course that's the lingua franca. But when I came here, yeah, I just I had no idea how to pronounce that. I pronounced everything in the wrong way. Whereas you're lucky if you want to come in my country, in Italy, and you learn the alphabet and each sound of each letter, you can already, well, you want to know what you're saying, but you can read Italian quite fluently, because for every letter there's only one sound, that's it. That's quite handy. Please do something about that. Oh, well, he's right. I mean, Seraphim is right. It is mechanizable. In fact, in Italy, we had a software called Air Finestra, meaning the window. I think it was done during the 90s, and it was already readily available, right? It was a software, you put text in, and you get the right sound out of it, okay? It was quite convincing. It was quite convincing Italian. I think that for that to be ready in the English language, you had to wait a little bit. Okay. A nice video about what I told you until now.
5,000 years ago, mankind invented writing, a way to record and communicate ideas. These simple marks on clay and paper changed the world, becoming the cornerstone of our intellectual and commercial lives. Today, we may be witnessing the emergence of a new medium whose influence may one day rival rapid writing. These are the electronic markings inside a computer. The patterns they form represent thoughts, concepts.
Okay, what is this video about? It's just telling you that the clay writing, the clay, marking, is no different from what we do with our artists. We have only two symbols to stay for a large number of strings, right? So it's a binary system. It cannot get more simpler than that. But that's exactly what we're doing. It's qualitatively no different. It's qualitatively exactly the same as writing on a clay tablet. Okay. So once you have symbols, it is quite straightforward to realize that you can manipulate them. You can do computation. So already in the ancient world, they realized that that you can use a piece of hardware, put your symbols in them, manipulate them according to some rules, and get the right output. Okay, in this case, then the number you want to compute in the end, right? So, of course, first, before getting to our computers, we had to figure out some mathematics, okay? And so, yeah, much of the ancient mathematics was figured out in India. And, the Indian invented the zero, which, of course, we needed in our binary system. But it's not straightforward, the concept of zero, right? Because, when meaning was really quite attached to the symbol, right? You could count one. Okay, one is something that I can see, okay? It's something there, it's one. The concept of one is bounded to the presence of one object, okay? Two, the same, any positive number is quite, okay, it's more straightforward to figure out. But zero is different, because it's the absence, there's nothing there. And it's quite hard to symbolize nothing. For us, of course, it's quite simple now that we know this. I mean, we use it since we are children. But in the ancient world, it was hard to figure that out. Okay, already the binary system was used by Pingala in the ancient world, and Aryabhata. I don't know how to pronounce it. He invented positional notation. Now, why is it important? Because, okay, you have your numbers, you want to represent them. But for computation, okay, the representation is quite important because it establishes the rules you can apply, okay, the manipulation of the symbols. When you have the positional notation, okay, adding, for example, becomes quite simple, right? So if you have position notation, means that at every, I'll just try to make this work. Oh, good. Okay. Oh, fantastic. Okay, so position notation. So we write numbers down like that, right? But even that is not straightforward. Why should we write those numbers down like that? Okay, we can express the same number in as a combination. I don't know. Well, of course now I'm going to use position notation, so it will end up anyway. So, but we can express the same number in many other ways, right? Like logarithms or other stuff. Okay, but this position notation, okay, the position of the symbols is important, and it tells you a lot about the number you want to express, and it helps you in computation.
We can't see the top.
Wonder of technology. I don't know if you can read it. Okay. In position notation, you multiply each number for a power, okay, for a power which depends on the position you're in, right? But when you do that, then of course adding becomes very simple. You just have to apply a set of rules, right? You learned how to add numbers at the elementary school, right? This is the name here, right? Elementary school. Primary school is elementary now. So in primary school, you learn the algorithm, but it's really an algorithm, okay? You learn how to combine these numbers, okay? What you do here, okay, you know that 9 plus 1, you have to write 0, and you have to take 1 in your mind and add it to this, but this is an algorithm, okay? You're not thinking about the meaning of the number, you're just applying a mindless set of rules. And this is possible thanks to positional notation. So thanks to this guy, this Ineka. Okay. So after we have that, so we have the 0 fully full-fledged. How do they call it? Fully operational. So you have the right notation. You have the fully operational 0. You have symbols. You can actually start to do a bit of mathematics. Of course, other cultures taught about mathematics and algorithm as well. So in China they had this mathematical art tome, okay, and if you read that, it's filled with algorithms that you can use in your Chinese life at that 202 before Christ was born. You have algorithms, so this document tells you, okay, you have a field. The field is long 12 Chinese units of measure, and width, the wide, blah blah blah, and you can get the area, you know. And of course, so they already figured out the algorithmic part of it, but I don't think they thought about the theory behind it as much as the Greek guys did. Well, now an interesting fact for so you know Donald. Okay, it's interesting for me. You know Donald Knuth, right? Donald Knuth? No? Yes. Donald. Okay. He wrote the you know. Okay. He wrote The Art of Programming, right? Is that the name of the book? I'm not sure. Okay. Well, he's a fantastic programmer. Okay, he wrote a lot about the theory of programming. And if you read these books, I think they're 3, but maybe then exploded to 7. I don't know. But it's all about algorithms. Okay, it's a collection of algorithms you can use, you can understand. And for a computer scientist, well, if you read all of that and you understand all of that, then you're good to go. So that guy, he was given some museum, I think it was the British Museum, asked him to decode the clay tablets from the Mesopotamian civilization, right? Because the historians couldn't, okay? Because they were actually highly mathematical. And they thought, okay, maybe some mathematical, some mathematics can decode them. And Donald Knuth actually decoded them and found algorithms. He found algorithms on the clay tablets. It's just, I mean, these guys were really advanced. Okay. Okay, we talked about the mathematics. So in the Greek world, they thought about it more theoretically. Okay, they asked the big questions. They of course they had a lot of time to spend thinking because they were quite a rich civilization, and they were democratic, so many people had access to wealth. And they asked the right questions. Okay, so Platone started to think, okay, we have these languages, this language, okay? And given that now we have symbols, that the language was objectified, okay? Meaning that you had language down in hardware, you can observe language. If you don't have that, it's really hard to objectify language. For you it just sounds, and temporary, it fades, okay? It becomes something that it is there here, it is there now, and it's not there in a moment, right? But when you have it written down, you actually start to think about language as an object. And that's what Plato did, right? And he says, okay, we have this object, this language. What can we do with it? So what are the limits of language? What's the nature of trueness and falseness? What's the definition, okay? So he asked the big questions. And his student, Aristotle, developed on that, and he invented the syllogism, which is another great feat, okay? It gave, at that moment, logic was born. And to build a digital computer, you need logic, and I will tell you about that later. And it is already symbol manipulation, because in the syllogism, you don't really care what you're saying, okay? What you care is that if I start with true premises, I end up with a true conclusion, okay? But you don't really care about the specifics of what you're saying, right? And you really, really need to objectify, to see language as a thing, to do this kind of reasoning. There's this guy, I cannot remember the name, I will tell you next time. But okay, there was this researcher, this scientist, which studied quite recently, I think it was in this century, past in the 20th century. He studied literate and unliterate people in Russia, okay? So there were quite a bit of literate and literate and illiterate people, so people who can read and people who cannot read, okay? And they think differently. If you present a syllogism to an illiterate person, at least in Russia at that time, I think it's probably, it's not Russia. So if you present a syllogism to an illiterate person, he will just not get it. For example, a typical example was he used like I saw all bears are white in the Arctic. I was in the Arctic and I saw a bear. How was the bear? White. Okay, it follows from the premises. Okay. If you present that to an illiterate person, that person would the typical answer he got from these people was, I don't know. I just saw black bears in my life, so I guess it's black. Okay. But already, if you have a minimum of literacy, okay, minimally literate people could already follow that. Okay. So really, the point is the objectification of language. Okay, so there's a nice story. There are many nice stories in Greece where if you say the wrong thing at the wrong time, you really mess up. So this Hippasus apparently discovered irrational numbers. So up until that time, the Greeks mathematician knew only about natural numbers and rational. Rational number is a number, I think you know it. I'll tell you anyway. No. This is a rational number. This is a rational number. Okay? Whatever number you can express as a ratio of two natural numbers. Okay? But this guy, Hippasus, he discovered that this number is not rational. He proved that it's not rational. I'm going to do the proof. But for that, he was drowned. The Greek mathematicians were really pissed off. Were really, really pissed off by that. And they just drowned him. Why did you even tell us that? And they drowned him, apparently. Yeah. That's really nice from that. So, now a big milestone in mathematics. Come on, guys. A big milestone in mathematics was when the Greek philosopher Euclid started to formalize the little mathematics he had at that time in axioms, okay? And combined these axioms to form propositions, okay? So he axiomatized mathematics, which is a powerful approach, And mathematics right now, the foundation of mathematics is axiomatic, okay? Now I think the main current now in mathematics is called formalism, which is basically, okay, I have a set of symbols, I have some rules, I combine these symbols, I get formulas. I choose some formulas to be axioms, and all I have to say combining those axioms, okay? And that's the point we're at in mathematics. Now, I think the axiomatic, the most used axiomatic system is the Zermelo-Feinkel with the axiom of choice. And that's the foundation of mathematics. So mathematics is built about these axioms, okay? So everything you have to say, whatever you have to say, you have to prove something, you have to go back. You don't have to. Modern mathematicians often don't do that, but you have to be prepared to do that if somebody asks you to, because you have to prove that what you're saying follows from the axioms, okay? Oh, we have a little bit of engineering already at that time, the Antikythera mechanism, right? So it was a specific purpose, not a general purpose machine. It was analog, it wasn't digital. And it was used, apparently, because I don't know how these guys figured that out, given that we only have bits and pieces. So apparently it was used to predict the movement of the stars. Okay? Yeah. Okay. So the Greeks started to ask questions about what you can do. What can you do with language, okay? But already they understood that there were limits. Something wasn't quite right. You cannot do everything with language. So Zeno is famous for his paradox, basically saying that if you have to cover one distance, you first have to cover 1/2 of the distance, then 1/4 of the distance, then 1/8, 16, 30. Okay. So his argument was, and seemed quite solid at that time, that you will never reach that point, because of course you have an infinite amount of bits to do before reaching that point. Of course, then somebody proved that with I think it's geometrical series, some converge, and they converge to the point. But already it showed that you get weird things out of language. Not everything follows, simply. In fact, during the medieval time, many people were endlessly discussing about God, right? They were really trying to form a theory of God. They wanted to talk about God, right? What is God? It is the most powerful being. He can do everything. Everything? Can he destroy himself? Yes, of course. You can create a movable object. Can he have the power to move that object? Of course, but then it's not unmovable. So he's not, he cannot do everything. And the argument, if I remember correctly, in my philosophy classes, is that he just can't. There's no resolution. And this is because they were using language, well, I would say wrongly, okay? They were hitting some hard limit, okay? The language, this language thing wasn't formalized enough to understand that you can stumble on every kind of contradictions if you're not careful. Okay, at that time my university was born, and happy birthday. That's a huge feat in science, mathematics, because universities are hubs, okay, where people can talk and discover things together. It's nice. So in my Hackintosh I tried to put another guy here, but then of course it didn't work. The passage from my Hackintosh to the iPad didn't work, and there is not that. So at that time, okay, while in the Western world we were stuck with Thomas, in the Eastern world somebody was making progresses, and Algorithm. If this sounds familiar to you, it is this Persian mathematician. And the word algorithm sounds like algorithm for a reason, because he's the one. He's the one. He invented the algorithm, which is a procedure, the application of rules to perform some computation. Because his work was so famous. Oh, he introduced the positional system to the Western world. So the other guy invented it, but he introduced it to us. Okay, so it was quite nice of him to do that. And yeah, so he made this algorithm, and the word algorithm comes from his name, algorithm. Of course, you don't need to know that, but I told you anyway. Okay, now we get to the good stuff. The Renaissance. In the Renaissance there was an explosion of science and the quest for knowledge, right? And it is quite nice that they were thinking about building a general purpose computer already. It is in the other slide, but I will talk about it. Okay, René Descartes, I don't know how to pronounce it. He came up with the hardware-software division. Okay. He said that, according to him, there's a res cogitans and a res extensa. The res cogitans means literally the thing that thinks, and res extensa is the thing that is extended in space. Okay, so in his mind, he thought that one thing was the body, okay, the physical realization of things, and one thing is it's the mind. So the controlling, he thought about an homunculus, he called him, a little man inside the brain at the center of the pineal gland, commanding everything. This is already a division of software and hardware. Yeah, that's of course how we got this, matrix, source code, avatar, with the mind being programmable. What you're saying is that your body is one thing, and your mind, the computing thingy, is another. And they hold the right from this idea. Galileo, basically is the father of science, of the scientific method. So already, they in the Renaissance, they started thinking about machines carrying mental operations, okay? So the first was Blaise Pascal. He made the Pascaline to help his father with computation. I think it was just addition. And then Leibniz, which I will introduce him to you in a moment, perfected it. But so let's see this video.
The French mathematician Blaise Pascal invented a calculator machine called the Pascaline in the early 1640s. More than 50 prototypes were created with 580 designs.
Sorry, I don't have access to any.
The operation of the Pascaline will be shown first, and then the mechanical design will be presented. On the top of the calculator is a series of input dials and output windows. Each input dial is divided into 10 parts by a set of spokes. A digit is entered into the machine by placing a stylus between the appropriate spokes and rotating the wheel clockwise until a metal stop is reached. Entering several numbers consecutively causes their sum to be displayed in the output windows. The value stored in the Pascaline must be cleared before a new series of additions can be performed. Clearing is done by setting all the accumulators to 9 and then adding 1 to the lowest order digit. Setting each accumulator to 9 can be accomplished by inserting the stylus between two specially marked spokes and turning the input dial all the way to the metal stop.
So in the Pascaline, you can see the first overflow, integer overflow, right? So you have this 999. You know, if you want to get again at the 0000, you have to have the 999 and then add 1 and the integer, you know.
Adding 1 to the lowest order digit causes a carry to ripple all the way down the machine, and zeros appear in every output window. You cannot perform subtraction directly on the Pascaline because the input dials only rotate in the clockwise direction. Instead, subtraction is performed indirectly by using a trick known as 9's complement arithmetic. The 9's complement of any one-digit number is 9 minus that number. For example, the 9's complement of 6 is 9 minus 6 equals 3. In a calculator with n dials, the 9's complement of a number a is 10 raised to the nth power minus 1 minus a. And therefore, the 9's complement of a minus b is 10 to the nth power minus 1 minus a minus b, which is equal to 10 to the nth power minus 1 minus a plus b, which is equal to the 9's complement of a plus b. The output drums of the Pascaline actually show each digit and its 9's complement, but a sliding display bar is used to cover one or the other. To subtract two numbers on the Pascaline, you must first slide the display bar down to uncover the 9's complement values, and then enter the 9's complement of the minuend. If you do not have the 9's complement of each digit memorized, you can simply place the stylus between the specially marked spokes and rotate clockwise until the stylus is aligned with the digit you wish to enter. The subtrahend is then entered in the normal fashion. The correct result is now displayed in the output windows. Because our inputs were only 2 digits long, we only consider the lowest 2 digits of the output. Looking inside the Pascaline, we see 5 sets of nearly identical mechanisms. A pair of crown wheels transfers the rotation of the input dial to an accumulator wheel. A backstop pawl meshes with the accumulator.
Okay, I think it's enough.
Are
you really interested in that? Do you want to know more? We hit the sweet spot a minute ago. Okay, now the 9 step. Okay, I'll just tell you about these guys, and then maybe we can do 5 minutes of. I see you a little tired. Okay. So, Leibniz. Leibniz was the guy who figured that out first. He wanted. I think I wrote down a citation from this guy. A quote, sorry, no citation. Yes, I did. So this guy, he understood that if you had a set of symbols expressive enough, right, and if you formalize the rules to combine them in the right way, this language will be really powerful, okay? You could devise algorithms to perform any kind of computation. So he really wanted to invent this language, and he worked on it. He did. He worked on it. He worked on it. He just didn't find it because he didn't know some things that were discovered later. But he wanted to mechanize computation. He had the idea during the Renaissance. Okay, so we're talking centuries ago. He wanted to invent a computer. So his plan was to do this language, and then to mechanize it. In fact, he worked on the Pascaline. Okay, he implemented addition, multiplication, and division. So he really had an idea. Okay, on how to transform from symbols to machines. Okay. And he wanted to mechanize language. And in fact, he understood that in that time they were slaves of computation. Because, of course, any computation they had to perform themselves by hand. They had huge tables of numbers, and they could combine them. But every computation they needed to do by hand. So imagine being a merchant at that time. Most of your time will be, adding numbers, which is, is more fun ways to spend your time. So Leibniz wanted to invent a certain script of language that perfectly represent the relationships between our thoughts. The characters will be quite different from what has been imagined up to now. The characters of this script should serve invention and judgment, as in algebra and arithmetic. It would be impossible to write, using this character, chimerical notions. With chimerical, he meant something that is not specific, something that can lead to paradoxes. Okay? So he really understood what should have been done. Of course, there was no technology at the time to do it, and there was no, the mathematics, the logic was not ready, okay? So he really couldn't do it at that time. He invented calculus together with Isaac Newton, which of course is, I would say, is the main tool right now for engineers, okay? In fact, I think it's one of the first exams, the first courses you follow if you do engineering is calculus, multivariate calculus, and yeah, of course, he discovered the laws of motion, and it was unpleasant, Newton. So he was a great scientist, and really our civilization would be much different now without him. But apparently, he wrote his books, Principia Naturalis, Naturalis Principia Mathematica, or Philosophia Naturalis Principia Mathematica, or Principia, they call them. So he wrote them so that no lesser mathematician could read them, right? Which is kind of, come on. You do it for everybody, so everybody can. So it wasn't an open source, kind of that. Okay, so I would say maybe we can do 5 minutes of revolution data. So in the Industrial Revolution era, right? That time, well, we have exciting stuff, but they're mostly engineering related, okay? Because of course it's an industrial revolution, so people really saw what machines were capable of. So they created a lot of automata. Of course, they created a steam engine and all of that. Again, so we had Leibniz in the Renaissance. Again, here we have Babbage. He really could have built a general purpose computer. He could have built, in the 20th century, he could have built a computer like we know today, right? He had all the theory figured out, well, mostly, okay? So at that time, you have this French guy, José Marie Jacquat. I don't know if I pronounced it correctly. What he did is basically invented punch cards, okay? So IBM will tell you we invented punch cards, that's not true. So IBM just copied the design of that guy. So he had these punch cards, invented this loom which could read punch cards. So he could weave with this loom whatever pattern he could think of. So he programmed Okay. That's a nice tune. So he invented a programmable loom, okay, which by itself is not anything to be excited about, but it's the concept of programming, okay, that finally came about. And Babbage really used this. So Babbage was an interesting guy. He's the most nerd character you can think of in the 20th century. So he was proper nerd. He was interested in things that you cannot imagine. So he did a lot of stuff. He was a brilliant mathematician. He went to Cambridge. He really despised Newton because his notation was just awful. So Newton didn't do anything to help other mathematicians understand him. And he really was, so Babbage really was against the Newton culture, because Cambridge at that time was really
Newtonian.
The mathematics there was just an echo, you know, they were just repeating and kind of, you know, adoring Newton. So he was a brilliant mathematician, and again, in Cambridge, he had a club of Newton haters, basically, if you really, it was that. And apparently the story goes like that. He was talking with his friend, and he says, you know, he's doing this mathematics, probably either a proof or some calculations or computation. He was saying to this friend, I really hate this, okay? I'd really like to have a machine to do this for me. Why cannot we use machines to compute other than just do physical labor? And the friend says, well, this is quite possible. That's apparently the quote. And he did think about it, and he built a difference engine, okay? He built first a small prototype of the difference engine. So it was an engine. It was gears, and you would action them by hand, and this engine used the method of differences in mathematics. So basically the concept is you can approximate, well actually you can calculate polynomials, okay? And you can use that to approximate any function, and well, not any function, many functions, many classes of functions could be approximated with a difference engine, okay? Why did he do that? Because he wanted to create this machine, okay? He wanted to create this machine to compute, to do mental work with the power of steam, okay? So the government was interested in that. Why? Because of course, so okay, at that time you used numbers, of course, okay? And you needed numbers to compute. But as I told you, given that there was no general purpose, well, even specific purpose, computer to spit those numbers out when you needed them, you had huge books of numbers, okay? That is huge tomes. And they contained errors. That's a problem. Because a little error in a numerical computation, in a book, could let some navigator in each ship to just crash upon some isle, okay? It was a problem, okay? And Babbage was proposing the solution, and the government wanted that, and they shoved him a lot of money, okay? And they did that. Apparently, in the end, when they stopped giving him money because he was a terrible manager, they spent £17,000 at that time, and I thought, okay, this is not huge. It's just, you know, I can do that in a year worth of work. And then I did the conversion, of course, on the internet. It's apparently £1 million. Okay, so they gave this guy £1 million. Okay, just do this machine for us. Okay, speed out those numbers. We need them. So he failed. He did plan everything for his difference engine, but he wasn't an easy guy. So he had an argument with his mechanic, basically. And the mechanic says, screw you, I don't want to work with you anymore. And so the government already spent £17,000, and when they heard about this, and the lack of progress, because he worked on that for I don't know how many years, the government just said, okay, I'm shutting down this, okay? They did a huge mistake. They did a huge mistake. Because Babbage was already working on the analytical engine. The analytical engine, with other bar, the analytical engine, if he were able to produce it, to build it, that would have been the first general purpose computer, would have been that computer, of course, with the mechanical technology of that time, but it could compute any function that a computer now can compute, right? So it's a general purpose computer. But he wasn't very verbal about it. So it's a case which really shows that PR pays out, okay? You have to say this stuff. You cannot just say, yeah. So he wasn't verbal about it, so the government shut the program down. He had the plans, and Ada Byron helped him at the time. She was a brilliant mathematician. She was just a genius, and she knew that. And if you read her letters, half of them is just, oh, I'm really smart. You cannot start to understand how smart I am, blah, 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 blah. And of course it made sense at the time, because a woman at that time wasn't even allowed to go to a mathematics course at the university. She could do botanics and home stuff. And yeah, it was sad, because this woman was really a genius. She helped out Babbage, and if they were given the technology, the money, the time to actually build that, I don't know, we will probably fly in spaceships around by now. I mean, the future will be shifted by a good, chunk. So yeah, she invented the first algorithm on a digital computer, so that they had this plans for the analytical engine. It was never built, sadly, but she's the actual first computer programmer. She invented that. And this is really a sad story for computing, because after they shut down the program, they figured out a lot of things, okay? A lot of computation theory, let's say, okay? They really had something going on, but when they shut it down, all that knowledge was lost. So when we started again thinking about this stuff in the 20th century, in the 1900s, okay? We had to start from scratch. So it was really, really bad. Oh, but by the way, they built the differential engine. There is one at the Science Museum in London. I don't know if they will ever build the analytical engine, because apparently the plans are there. They're not complete, but the differential engine, they were not complete, and guys figure out what was missing, and they managed to build it. So maybe we will see this analytical engine sometime. Oh, video.
Divide the circumference of a circle by its diameter, and you get pi, a number which never ends. A modern desktop computer can calculate the decimal expansion of pi to any number of places. To do it to 707 takes just 7 seconds. Remarkably, this same task took an English school teacher named William Shanks 28 years of his life back in the 19th century. At night, Shanks would toil at the long calculations, which got harder the further he went. Tragically, he made a mistake at the 528th place, and so the last few years of his efforts were in vain. In Shanks' day, the word computer referred not to a machine, but to a person who calculated. It was a tiring and unpleasant task, the mental equivalent of hard labor. The few aids available to such a computer, like the slide rule, were not very accurate. So mainly he relied on tables, books full of them with ready-worked multiplications, squares, and cubes, and shortcuts like logarithms. And inevitably, he made mistakes.
Typically, if the computer wanted to perform a multiplication, but first he would take the number, he would need to look up the logarithm. He would then copy that out from the table onto a piece of paper. He would then look for a second number, look it up in the table, copy it out, again transferring it onto paper. He would then perform an addition, he would add the two numbers, and then refer for yet a third time into the table to look up the anti-logarithm, the reverse of this process, and then copy the result down again. There is every opportunity for error in every stage of that operation.
And even if the human computer didn't make a mistake, the tables he used might be riddled with errors, since they too were prepared by computers. When new sets of tables were produced, mistakes were always found. Such errors became an obsession with the Victorian mathematician Charles Babbage. When he ordered new tables to be calculated, he had the figures done twice by two independent human computers and checked one against the other.
The Astronomical Society had appointed a committee to prepare certain tables. We had decided on the proper formulae and had put them in the hands of two computers for calculation. We met one evening for the purpose of comparing the calculated results.
54, yeah. 63, 18, 55.
Correct.
67, 38, 45.
Sorry.
I've got 61, 38, 45. Valid. They're on mine. Right. 67, 38, 45.
Finding many discordances, I expressed to my friends the wish that we could calculate by steam, to which he assented as within the bounds of possibility.
The Victorian age had seen machines taking over all kinds of physical tasks. If, Babbage reasoned, machines could carry out physical tasks, why couldn't they do mental work as well? The Industrial Revolution was built on numbers. Developments in civil and industrial engineering relied on accurate calculations. So did navigation. The volume of traffic was building up between Europe and the newly independent America. There were reports of ships running aground because of faulty navigational tables. So Charles Babbage designed a calculating machine and built just this small section. It's set up at the moment to produce a sequence of squares simply by turning a handle. Reading vertically, 9 is 3 squared. 4 squared is 16. 5 squared is 25, and so on. Babbage called it a difference engine because the wheels and shafts added by a technique called the method of differences, which was comparatively easy to mechanize. To avoid printer's errors, the full machine would also print out the answers. Recognizing the national importance of accurate tables, the government put up the money to pay for development. But Babbage never completed his engine, partly because he was a poor manager, but mainly because he'd had a better idea. The difference engine could only do one thing: calculate by the method of differences. How much better, Babbage thought, to build a machine capable of doing many different things. With that single thought, Charles Babbage had hit upon the fundamental concept of the computer 150 years ago.
This particular piece was under construction at the time of Babbage's death. It was a small experimental piece that is all, in fact, of the engine that was ever completed. The largest design of this kind that Babbage devised would, in fact, be the size of a small steam locomotive. The machine is revolutionary in many respects. It has much in common with modern digital computers, which is what's quite extraordinary given the time in which it was designed. The mill, which is what we would now call the central processing unit, the place that the machine operated on information, is quite separate from what we now call memory, what Babbage called the store. The separation of store and mill is a feature of the subsequent electronic developments. Perhaps the most revolutionary feature of the whole machine is the fact that it's programmable. It's a general purpose programmable machine. And Babbage used punch cards to program the machine.
Babbage got the idea of using punch cards from the textile industry. The French silk weaver Jacquard had used punch cards to control a loom. The pattern of holes in each successive card controlled the position of steel rods, which in turn determined which threads of the warp should be lifted above the shuttle and which should remain below. Different sequences of punch cards produced different patterns. Jacquard even had a set of cards which wove his own portrait. But whereas silk weaving was all Jacquard's loom would do, Babbage planned to use the cards to get his analytical engine, as he called it, to do a limitless number of different computations. Throughout history, machines had been defined in terms of what they did, but Babbage was proposing a machine whose purpose would be up to the user.
That, I think, was a real profound difference in the way people thought of machines, because for the first time in history, you had someone designing a machine who didn't really think, as he was designing it, all of the different ways that it could be used, what it was good for. It was good for anything. And he would worry about that later on, but for the moment he would concentrate on getting the machine to work in a very general sort of way, and then having the specific uses attended to later. What we nowadays call software was really born in that moment when someone thought that you could separate out those two functions of a machine.
Babbage left hundreds of drawings of the machine's hardware.
That's why they managed to build it, the Science Museum. Apparently there was this Microsoft, ex-Microsoft guy, so he had bags of money and he didn't know how to spend them, so he went to the Science Museum and said, you have technicians, can they, help me out and build this for my living room? So they built it for his living room, but this guy said, yeah, okay, you can have it, at the Science Museum, just for this year, and then for another year, and then for another year. So we don't know how long that machine will be there, the difference engine. Actually, on YouTube, you have a demonstration, which is really nice. Have a look at that. It's really nice to see this machine works. You really can sense the fact that this a mechanical system, right? Physical system, which you can see the divide between software and hardware. That's what I'm trying to say. So yeah, we don't know how long that machine will stay there. So if you are in London and you just go to the Science Museum, see it, because otherwise you have to go at this guy's living room. Can be a problem. So, during the Industrial Revolution, during the 20th century, there was a huge crisis in mathematics, that really people started to see that the foundations of knowledge were falling, and this was the start of it. During the Industrial Revolution, these two guys formalized non-Euclidean geometry. So you have the Euclidean geometry, that guy we talked about, Euclid, with axiomatized mathematics, not geometry. Geometry, not mathematics. I think we did this axiomatization of geometry. Yeah, I think so. At that moment, geometry and mathematics were really the same thing. So these two guys say, Euclid had this axiom where two straight lines, if they're parallel, they never touch. They never touch. And they say, but what if they touch? What if we do without this axiom? What happens to the geometry? And weird things happen to the geometry. And actually, in our physical world, you cannot just say this is Euclidean geometry, because non-Euclidean geometry is locally Euclidean, meaning that, okay, with this geometry you can imagine a really weird shape, okay, a saddle-like shape, okay, and if you look at it, it's not, it's not linear, like Euclidean geometry, okay, the space is not linear. But actually, if you go to a point in that saddle, okay, in the vicinity of that point, it's perfectly Euclidean. In fact, it turns out that our geometry, the space we live in, is not Euclidean. Einstein, built his work on that, and yeah, we feel it is. It is not. And these two guys discovered that, and Bolyai made it the work of his life, and he wasn't credited at all with it. I mean, now we that is not his face. That is some guys. Yeah, some guys did an illustration of him, but he did have no data about him, right? So he just, yeah, that's Bolyai. Okay, that's fake. This is not him. And he died. Nobody knew about him, and he died mad. Of course, because he thought, I discovered, it should blow your mind. Why don't you, nobody cared. Lobachevsky, nobody cared. He died mad. Lobachevsky died half blind and he wasn't able to walk. So I tell you, never invent non-Euclidean geometry. I mean, it's really bad for your health. Okay. So during the Industrial Revolution, you have this engineering explosion, right? Okay, they mechanized physical work, and they thought, well, can't we mechanize communication? And they did, okay? Morse, Henry, and Vail, they invented systems of communication, which instead of using mechanical ways of communicating, they thought, okay, well, just use electricity, okay? Which is fast, it's much faster than a horse, of course. And they thought, okay, how do we communicate with electricity? And they invented their own system, some more complicated, some less complicated. Morse was one of the simplest ones, and it was the one to catch up. And it's a digital system, okay? With electricity, if you measure it, right? Well, the way he was using it, you will measure this electricity, and either it was there or it wasn't there. Okay, it's a binary system. Now, the Morse code itself is not binary. I think it's ternary. I had this discussion with Seraphin, because you have your dot, you have your how do you call it? Dash. Okay, you have your dash, and that's 2. But you have to separate the words, okay? Or even the letters, you have to separate, you have to put space in it. If you don't have the space, actually I did a little search on the internet, Can you actually understand anything if you crush everything, just binary? No, you can't. It's ambiguous, it's highly ambiguous. So you get things that you cannot understand, so you need a space. It's ternary. It's a ternary alphabet. Seraphim agreed, of course, because it's true that it's ternary, but it's implemented in a binary system. And that's something that really, really changed things, because that's what we do today, okay? We have many symbols, and we map them down to binary symbols, to the most simple symbol system that we have. And every set of symbols can be mapped down to some binary representation. Well, this, of course, you should know. Okay, we have Boole. He invented Boolean logic that you know, and I know that for sure, because if you programmed in whatever language, you always have a bool type, I think. Okay, in Java, of course, you have it. Is that right? I never programmed in Java.
Yeah.
Yeah. Okay. So, and okay, it's you use the Boolean logic in programming languages because it's useful. You have this set of okay. Why is it interesting? Because it's digital. In Boolean logic, you have 2 objects. Okay, you have 0, 1, and then operators on those. Okay. That's basically the concept of the logic. You don't have quantifiers, you have nothing. You have just 0, 1s, so stuff that is there, it's not there. True stuff, false stuff if you want, and operators in that. Okay? And it's not interesting only because now in every programming language you have that. But at what level do we have Boolean logic? Do you know that? You should know that. Someone tells me. So, where do you have logic gates? Exactly. That's Boolean logic. And actually, that idea, Shannon had that idea. We'll talk about it. He's a great guy. He had that idea of okay. He was playing with logic gates, electronic gates, and he thought, okay, we can treat those with Boolean logic. And by that, it really invented the current way we think about processors, okay? And we build processors. Okay, now a little bit about chaos. So at that time, the great scientist, Poincaré, discovered chaos. He was a polymath, okay, meaning that he contributed to many areas of mathematics. Great contribution to mathematics and arithmetic, whatever you can think of. Thought about the three-body problem, so Newton couldn't really figure out how to solve the three-body problem. He had a thought of that, but we're talking about him because of chaos. So he was the first one probably to witness chaos, okay? What's chaos? As I told you. So he had these equations describing some system, and he saw that from these equations, he couldn't predict the future behavior of the system. Because you have this exponential, I missed the words. Basically, you have a measurement, right? In well-behaved systems, you get some numbers out of your system. It's a measurement, okay? It's the state of your system. You have equations, you show these numbers to the equations, and the equations tell you what the system will look like after a little bit of time, right? More time, maybe. If the system is well behaved, let's say, you have a little bit of error in your measurement. Every time you measure something, you have a little bit of error. That cannot be, it's a physical, theoretical limit. But with good systems, let's say, if you have a little bit of error in the beginning, you have a little bit of error in the end, okay? With chaotic systems, if you have just a little bit of error, okay, just measure up. After a little bit of time, your prediction is totally bollocks. I mean, it doesn't tell you anything about the system. And I mean really, because it behaves quite stochastically, quite randomly. Okay? After a while, you have no idea what the system is doing. And that has huge repercussions on computation theory, because it means that there are systems that we really cannot treat with digital computation. Yeah. I mean, there are, this Blue Brain project, DeepMind, also in America, I think. This project, they get a lot of funds from the government. Like, I'm talking about billions, okay? I'm talking about a moderate amount of money to simulate a human brain, okay? But I told you, you have 3 neurons, already you have chaos, and already your digital system struggles, okay?
Could we have our next expert in the chair, please? Welcome to the show. Do you have your name, please?
I'm Chris Budd.
Okay, Chris, could we see your theory, please? Thank you very much. Your theory is that there is nothing random about chaos. Okay, what are your qualifications, please?
Well, I'm quite a scary person because I'm a mathematician.
You're a mathematician, okay. And your theory, there is nothing random about chaos. Could you explain that to us, please?
Well, some things in our lives are very predictable. For example, my watch. I know exactly what my watch is going to do in an hour's time. Other things are really random, like my dog. Now, when I let my dog loose in the park, it goes all over the place, and you've got no idea where it's going to go. But there are important things in nature which really look random, but are actually governed by quite well-defined scientific laws.
Right, and these laws are what are known as chaos theory. That's, broadly speaking, what it's known as.
Well, chaos theory describes things in nature like clouds, for example,
yeah,
which look random, but the theory behind them is actually quite simple.
The butterfly effect is part of this, isn't it?
Well, there was a theory which came out in the 1960s by a guy called Ed Lorenz,
Right.
and he was trying to explain weather. And of course, weather's quite difficult to understand. It changes a lot. And his theory was that if you took a butterfly and it flapped its wings in, say, Venezuela, then the small effect of the flapping of the wings of the butterfly could kind of grow and grow and grow, and eventually end up in a hurricane in Bristol, for example.
Right. I can't help noticing you've got a machine, Chris. What's that for?
Well, this is to demonstrate chaos. This is what we call a double pendulum. Now, it's very like my leg. So imagine that's my hip,
right,
and that's my knee. So that's the bottom bit of my leg does that, and the top bit does that. Now, this is a pendulum, and it's exactly described by very, very simple laws. It's described by Newton's laws. These are things you learn at school. And for a long time, it was thought that anything that was described by Newton's laws behaved in a kind of very predictable way. And sometimes there's the pendulum swinging the way we know pendulums swing. So that's behaving very predictably, and I could say exactly how long that's going to swing.
Right.
But let me show you some chaos. So again, remember this is simply governed by laws of mechanics, Newton's laws, and all we're going to do is let it go. There's no motors in here or anything, it's just driven by gravity. Just watch it go. Now, I want you to watch that and
it's got a certain symmetry to it, has it not?
you wait. Chaos occurs in all sorts of physical systems where we see really quite almost random looking and unpredictable behaviour, which is simply an outworking of basic physical law.
I'm afraid we're at the stage where you can
So is this the way the money markets are behaving just now?
Well, that's a very good question. The money markets are primarily driven by what's going on inside the brain. And we don't think that the brain can be easily described by mathematical formula.
I tell you what, man, after a while, looking at him, but really looking at that, we all just going to go agree, just go, yes, you're correct.
Swing for you.
It is all random.
Oh, wow.
What this shows us is that some things which, when you look at them on the face of it, they look really, really complicated, may actually be driven by quite simple rules.
I want one of these now, man. I want one of these in my house, man. I can invite a lady over that I fancy and have her stare at it, then I can go, I smell good, don't
So, who's first discovered this phenomenon and how?
Well, Newton wrote down his basic laws of motion, and for about 200 or 300 years, everyone thought that because Newton wrote down these laws, you could predict everything. And one of the main things they studied using these laws was the solar system. And about the end of the 19th century, a guy called Poincaré, who was a French mathematician, one of the really brilliant mathematicians of his time, tried to use Newton's laws to answer a really important question, which was whether the solar system would stay stable, whether we carry on orbiting the sun, or whether we go into the sun and blow up in a horrible mess.
Right.
And so he tried to predict the long-term behaviour of the solar system, and he found he couldn't. And the reason he couldn't was, again, the solar system obeys Newton's laws like this. But after a while, small perturbations grow and grow and grow, and you can get these really random effects going on.
I noticed just before every time you crack into a new element of your theory, you roll that out right there. Very clever, man.
It's fantastic. The whole of life is here.
But what about things like rooks going to a rookery at night, and the noise, and they're going hither and thither, and they're all over the place? Are they actually acting, not chaotically, but what appears to be random? Do they have a pattern?
Well, birds flocking are a really good example of what we call a complex system. And a complex system is where you've got lots of things all interacting very closely. So rooks or starlings is another really good example.
We can show you some starlings actually, Chris, if you can talk us through what's happening.
Yeah, so each of the starlings is responding to the air currents and certain visual clues from starlings quite close to them. And the combination of all those produces these wonderful kind of coherent patterns. It's what we call emergent behaviour. So where you have lots of things all interacting, but suddenly they behave like one big organism.
Is there anything else? Give us another example of a time of chaos that wasn't random.
Well, earthquakes are probably a very good example. So we're pretty sure that there are basic laws underlying when earthquakes occur. Earthquakes are caused by one rock face slipping over another, and that's friction, and that's reasonably well explained. But unfortunately, we know that even simple laws can produce these really complicated outcomes, and that's why it's really very hard to predict earthquakes.
So ultimately then, you cannot predict earthquakes, thus they are still random.
Well, there's a difference here between...
You might want to twist your thing around.
There's a difference between whether you can have a difficulty predicting something, it's very hard to predict that, or whether it's truly random.
Whether it's just happened by chance.
Yeah.
What practical applications does chaos theory have in our lives?
We've got lots of applications. One of the great things that chaos does is it mixes things up. So when you see this moving, you can see it mixing everything around. And there's lots of things in our life where we want to mix things up. And one of the things that I've worked on a lot is the design of microwave cookers.
Yeah.
And if you put food in a microwave cooker, a normal microwave cooker, the electrical fields can be quite irregular, and that can cause hot spots and cold spots in the food, which means that it cooks not very well. And the more modern designs of microwave cookers actually try to make the electrical fields chaotic, so that they kind of randomise more inside the cooker, and that gives you then much more even cooking.
Right, one last question. Is chaos theory the right name for it? You think? From what you've said, it sounds to me like it does it a disservice.
One of the problems with the word chaos is that it can kind of mean two different things. So to a non-scientist, chaos means complete randomness. Again, going back to my dog. My dog's a spaniel and therefore behaves totally chaotically all the time. But for scientists, chaos really means something rather different. It's this unpredictability that you get arising from scientific laws. And we can't get away...
Okay, so we close with chaos.